All right. Good morning or good afternoon, everyone, depending on where you are. Welcome to session number 2 of Inorganic Ventures' 2022 webinar series. I'm Thomas Kazakowski, QC Manager here at IV, and I'll be moderating today's session. I hope you found my presentation from January helpful and informative for the work you do at your labs. Today's topic will switch gears and focus on a different kind of interference. But first, a few housekeeping reminders for those of you with us live today. Please put your questions for our speaker in the Q&A box at the bottom of your screen. We'll address these in our Q&A session at the end of today's presentation. If you have technical issues with the Zoom platform or something unrelated to the talk, please use the chat feature. We are also trying something new. In the chat section, you should have an option to view a shared Excel document you may want to download and look over at some point. It's the actual interference table referenced in today's talk and also what we built for use in our daily custom MEB check method. If you don't see it, wait until the end of the session, end of the presentation, and we'll repost it when we start our Q&A session. Now, I won't keep you waiting. Our presentation today is utilizing interference tables for complex ICP-OES methods by Mike Booth. Mike is currently the Director of Technical at Inorganic Ventures. In this role, he directs the activities of my group, Quality Control, in support of commercial manufacturing and ensures compliance with applicable regulatory and industry standards. He also heads up our R&D and quality assurance groups. Mike is an experienced chemist with expertise in quality control and instrumentation. His extensive knowledge involves areas including ICP-OES, ICP-mass spec, ion chromatography, and various titration techniques. Mike holds his Bachelor of Science in Chemistry from West Virginia University Institute of Technology, better known as WVU Tech. I will now start us off with a polling question, so listen up and key in your response. Our question for today: do you use an interference table for any methods that you run in the lab? All right, it actually looks like everybody has answered. Not sure if that shows up for everyone or not, but looks like pretty good split. Yes, a lot of people are using interference tables and about half of us aren't, and some of us are not quite sure. So keeping those responses in mind, let's see if we can learn more about how interference tables might benefit your lab. I'll now turn it over to Mike.
Good morning, everyone. My name is Mike Booth, and I am the Technical Director at Inorganic Ventures. Today, we will be discussing utilizing interference tables for complex ICP-OES methods. So let's go ahead and get started. Together, we will review the process of combating spectral interferences by constructing an interference table to ensure your results are as accurate as possible. We'll review what a spectral interference is and what constitutes an interference table. We will also discuss the types of methods that could benefit by adding an interference table. Finally, we will review in detail how to construct an interference table. First, let's answer what is a spectral interference. A spectral interference occurs when multiple elements share the same or a very close emission wavelength. Since different elements will usually have different intensities on shared or close emission lines, some spectral interferences can be barely noticeable, while others can cause serious issues for data analysis. This slide demonstrates a classic example of what we use at IV when discussing trace metal impurity testing. The sample in red is a supposedly high purity iron solution being run on an ICP-OES at a concentration of 2,500 ppm. During data analysis, our technician found a peak that was present that the instrument software characterized as zinc. To confirm this impurity was present, the sample was rerun on the ICP-OES with a 1 ppm zinc spike. As we overlay that zinc spiked sample onto the spectra in blue, you can see that the red peak is indeed iron and not a zinc impurity. So why did the software call the peak in red zinc? The answer is most likely that the method had not been updated with the newest wavelength calibration or had improper peak centering. For reasons like this, our quality control technicians at Inorganic Ventures manually review almost all spectra and use raw intensity data whenever possible. It is our practice to have control over instrument data in the most detail possible for the most accurate, in-depth analysis possible. Now that we are all on the same page about what constitutes a spectral interference, let's review what an interference table is. I've defined an interference table on this slide, but this is just my personal definition. You or your method's definition may be different, but to cut through the noise, an interference table is just a data interpretation tool. How you decide to use that tool is up to you. You may decide to validate your interference table and use it to calculate final sample results, or you may simply use it to help troubleshoot tough samples. I'll show an example of the interference table that we have constructed, and you should have the ability to download a digital version of the table via the Zoom chat. I've listed some types of methods that may benefit from having an interference table available to reference. This is by no means a definitive list, so as we continue to discuss how interference tables are used, think about the methods you run and if having extra information on possible spectral interferences would be useful. The method that we will be reviewing in detail today will fit into this highlighted category. Inorganic Ventures supplies a wide variety of custom certified reference materials which all require QC testing to ensure the blend was manufactured correctly. Our QC department will test 40 to 60 different blends each day, so a method was created to help cover the volume of samples and help troubleshoot any failing results to either confirm the result or pinpoint any bias that may be present. The next two slides will demonstrate a portion of the variety in the samples being tested using this new method. These two blends show an example of some of the easier samples to test. We have the extreme luxury of knowing what to test for and what concentrations to expect. Both of these blends only require a single prep to run on our instrument, and the largest difference between them is the concentration and the number of analytes that should be present. This blend is an example of a little tougher sample to test. This has a variety of concentration that requires two preps to ensure all analytes will be within the range of the calibration curve. When the second prep is examined, we will have to keep in mind the analytes at higher concentrations that are present in the blend and account for any spectral interferences that could arise. This slide shows the final calibration curve for the custom product testing method. We ended up using three main calibrations, each having a 4-point calibration curve. These curves were grouped to avoid spectral interferences and ensure chemical stability and compatibility at the high concentration levels. The work to develop and validate this method has paid dividends by decreasing the amount of initial test fails due to interference or matrix issues. The concentrates that we use to make the calibration standards are actually available for purchase from Inorganic Ventures as customs. So if you're interested in this method for your lab, please reach out to us about the products we have listed in the chat. As good as this method has turned out to be, it is not without some flaws. So we decided to add an interference table to help our technicians better interpret the data from complex blends. Now we are going to begin constructing an interference table one step at a time. Before you get started, there are two preliminary steps that you will need to do. The first step is that you need to have a method built so that you have all of the emission lines selected that you wish to use. And just as importantly, the method must be set so that your peak centering and baseline points will remain in place as you periodically run wavelength calibrations on your instrument. Your method should also be consistent in terms of the instrument settings for the plasma condition, like RF power and the gas flows. The method that we have built for custom product testing is actually the only method our QC department uses where they do not manually center peaks or set baseline points. This method utilizes the instrument software to calculate these points to make sure that our interference table will continue to be accurate over long periods of time. Second, you will need to run high purity single element standards so that you can measure the response on each emission line of your method. Cleanliness is key to ensure that interferences you may measure are truly spectral interferences and not just the presence of an impurity. Let's start building our table by running our high purity single element standards at a concentration of 80 ppm. For this example, we are going to examine spectral interferences on multiple lines using aluminum, cerium, iron, samarium, and thorium single element standards. Next, we will monitor the response on the radial 417.204 nanometers gallium emission line from each single element standard. You can see that only cerium produced a response equivalent to 4.5 ppm gallium. Next up, we will look at the axial 335.863 gadolinium line. Only thorium produced a response for that line that would correspond to 9.4 ppm of gadolinium. The next line we will review is for 259.372 manganese, an axial view. This is a pretty clean line with little interferences, so only iron produced a response which is equivalent to 0.1 ppm manganese. Next up is a line that is subject to a lot of spectral interferences. As you can see, cerium, selenium, and thorium all produced a response on the axial 360.955 line for palladium. Samarium shows just how extreme the spectral interferences can be by producing a response on the palladium line equivalent to 121 ppm. This interference is over 40 ppm higher than the concentration of samarium that was analyzed. Also, keep in mind that all of these interferences can stack on each other. So if your method contains emission lines that are subject to lots of spectral interferences, it can be difficult to determine what is the exact cause of any biased results. Finally, we will complete this example by examining the axial lines for 422.532 praseodymium and 220.449 tungsten. As you can see, the spectral interferences are due to samarium and aluminum, respectively. So now you have a taste for how tedious and time-consuming building an interference table can be. The graphic on this slide represents the interference table we built for our method. The yellow block represents the table that we built on the previous slides, and the blue block represents the size of our full interference table to scale. The results for our samples are exported into a method-specific Excel sheet where we have added the formulas necessary to transform the data from the interference table and apply it to the specific custom product that was tested. This process is similar to determining inter-element correction factors, or IEC factors, for ICP mass spec methods. So now that we have put all this work into creating an interference table, the big question is, does it work? The table on this slide is pulled directly from the Excel worksheet that we use to summarize results for our custom product testing. This section of the sheet details the results while not accounting for interferences from our interference table. For this blend, we see that our method uses 8 silicon lines and 0 lines are producing passing results within the 10% tolerance of the blend's made to value, with the closest result on a single line coming in at 13.64% off from the made to value of 1 ppm. Now let's add the portion of the sheet that accounts for interferences using the interference table we have built for our method. Utilizing the interference table, we can see that one of the 8 silicon lines now pass within our 10% tolerance. If you look closely at the table, you will also see that we have improved our percentage of pass lines for ruthenium, samarium, and selenium. But perhaps the most interesting change is that we have seen worse results for tellurium. We went from 5 out of 6 lines passing for tellurium to 2 out of 6 lines passing. Overall, as we have used our interference table for custom products in the past 12 to 18 months, we have seen a marked improvement in troubleshooting problems with blends that fail testing on our newly constructed testing method. We have not validated the interference table to allow our technicians to pass a blend based only on the calculations using the interference table, but the time spent on data analysis and planning a secondary test to confirm or dispute a failing result have been significantly decreased. In summary, we have reviewed what spectral interferences and interference tables are. We have talked about what methods might benefit from using an interference table. And finally, we constructed a very small interference table. We always like to recommend to people that processes must be fit for purpose. The same advice applies for creating your own interference table. As you have seen, the process of constructing a detailed interference table is lengthy, but the data can be invaluable to certain processes. If you have any questions deciding whether you should implement an interference table for your method, please reach out to our technical support team and they can provide additional advice. Before we end this morning, I want to take a chance to point everyone towards the Inorganic Ventures website. There is a wealth of technical information in the forms of guides, papers, and other resources, including a technical forum where you can submit questions or search previous posts. This concludes today's presentation. I want to thank you all for your time, and I would be happy to answer any questions. Thank you.
All right, thank you, Mike. For those of you with us, please continue submitting your questions in the Q&A box, and we'll answer them until we finish them all. We don't have many quite yet, so we'll start off with one from Mark. Are you willing to disclose which ICP manufacturer and model that was used to collect this interference data? Each manufacturer has a different library and emission response.
Yeah, sure. So that's an excellent question. You're 100% correct about that. The interference table that looks like again was just posted into the chat was developed using an Agilent 5110. It was the axial and radial VDV, so it was able to switch between axial and radial viewing modes. It's not the simultaneous one; it's the one that does it, sort of axial and then radial, depending on how you set up your instrument. We are also in process of checking this interference table against a newer Agilent instrument. I believe that is the 5800. I don't believe there's any other terminology that goes on the end of that one. I believe it's just the Agilent 5800. But again, it's still the axial and radial viewing modes.
All right. Next up, I've got a question regarding axial versus radial. Do you get different responses between the axial and radial with your actual interference table? So I guess when you have calcium response, does it actually give you a different number between those two viewing types?
Yes, and you will see that if you review the interference table. They are defined. Can't remember exactly how it's defined in the sheet, but you are able to tell if it was the axial mode or the radial mode that was checked. I believe it just says axial radial, maybe slightly abbreviated. But you can see there are multiple examples of looking at the same line with both modes, and sometimes you will see different responses. Sometimes they'll be very similar. It really just depends on the line.
Probably a lot to do with background, I would guess.
Exactly. Yep.
We've got a screen share of the actual table.
Perfect.
So those of
Yep.
you
So
yep.
column C there details the viewing mode. So yeah, you are able to see exactly what is coming across. And actually, I believe you can look at lines 7. I believe that's 7 and 8 are the same. Yep, the same line for silver, but you see that chromium interference over there is about 30% different on the depending on the viewing mode. Exactly.
All right. Got another question from Mark. Can you define the elements that were done in radial versus axial? And
Yep. If you download the sheet, it is all there for you.
we did them all.
Yep.
Yeah, we when we developed this method, Mark, we decided to just do it all. That way, if some things went over range on axial, radial would also work. So we would have some a chance of having some passing lines. So that helped, and that's why we chose all lines, not just the ones that are radial normally.
Yep.
Right. Next one. Got one from Heath. Can we access a copy of the table that you generated as a starting point for reference?
Yeah, so we didn't have a table that we started with. In the past, we have used the software to sort of, as we suspected an interference, we would, use the software to help us verify that fact. But you guys can use this interference table that we have available for download as your starting point. It would put you probably a lot further ahead than where we were.
All right. Another one from Mark. It seems like most of these tables are completed in low HCl concentrations. Have you given thought of redoing this work on high TDS, high acid matrices?
That is correct. We put this table together in dilute acid mainly because that was the matrix of our samples. If you have a high TDS matrix that you run routinely, you would definitely want to use that as your matrix for the run when you run high purity single element standards. Again, now when you take into that account, you're also going to have to make sure that whatever you're using to make your matrix is also high purity, so that you're not measuring impurities from the matrix component or the single element component, but you're actually measuring spectral interferences that would be present. So we haven't done that work because our method is usually in dilute acid.
All right. Our next question is from Adrian. How do your tables compare to corrections that could be applied in the Agilent software?
So that is a good question. It is our preference in our lab that we try to refrain from using the software as much as possible to do calculations. We like to pull out as much raw data as we can and work everything up ourselves. It gives us a little bit more traceability, and it gives our analysts a little bit more visibility on what the data is, where it's coming from and what it looks like. So if they see a result that's not expected, they can sort of go back piece by piece and figure out what might be the issue. I believe there are ways to sort of build this information into the software, but we have not explored that with our instruments. We prefer to do everything offline.
All right. And just a note from Mark, we typically verify interferences against the NIST emission lines for known elements. Mike, can you give any thoughts on what those NIST emission lines would be?
So let's see, just a note. Yeah, I think there are some pretty well-defined libraries out there. So that's also I think a very good road to go down if you're looking to verify the accuracy of an interference table. There should be some pretty good libraries out there that would have even more information than what we've put together. And I think just sort of sourcing all that and compiling it and essentially making it fit for your purpose is key.
All right. So our next question, I'll throw another one out there for you, Mike. You had mentioned that you really can't change the peak centering and the background points in your method, or it kind of messes up the table. Can you give any feedback for those that might have issues with different manufacturers' way of handling wavelength calibration and keeping it consistent day to day?
Yeah, that is really one of the, again, since we like to do a lot of our data analysis sort of offline and manual, that was one of the, the harder sort of trials for this method, because like I'd mentioned it in the presentation, but we normally prefer our technicians and analysts to manually center peaks and set baseline points. It'd be a lot to ask for this method just because there are so many lines, so that having them do that every day would be extremely tedious. But it is something that you really need to account for. So I would recommend that you sort of reach out to whatever your instrument manufacturer is to help to get more information about how they set, how their software handles peak centering as you do multiple wavelength calibrations, because you will see over time that, as you run a wavelength calibration on we do normally do ours on a weekly basis, you'll see the drift occur, over months and years as you run your instrument. So if you're using the same exact baseline points and peak centering that you were when the instrument was, initially installed, and there's no other alterations to your method, your peaks are not going to be centered after a few months very well, especially after a year or so. So I would recommend that you reach out to your instrument manufacturer and get a little bit more detail from the software of how they handle that. If you are looking for a method that does that sort of automatically. Actually, it was Thomas who did a lot of the work setting that method up. So he verified, the baseline points and the peak centering would remain stable over time with this method.
Yeah, so it does depend on the instrument. So one of the things we noted with the Agilent software when I first developed this, there's actually a little checkbox in the method that we didn't know what it did exactly until we tried it out. It's a peak drift correction. So if you check that box and then you lock down your method, um, you run it once, center your peak, save it as a template. It actually monitors some lines like carbon and argon and nitrogen, lines that are always there because it's in the air and in your plasma. It actually uses those as a way to center all of your peaks. So it does like an offset. So if it sees that those shift a little bit the next day, it automatically shifts all of your data so that everything's properly centered. And it's been years. It works. We haven't had to recenter peaks. This template's locked down and it's working great. Every instrument manufacturer has a different way of doing that, but definitely reach out to them and see what they can do. I know some have wave cal solutions that you can run daily, and that would do the same thing. But just check with your manufacturer to see what their strategy is. All right, so we have some more questions, I believe. Does PerkinElmer have NIST emission lines? I don't think we're able to comment on that.
No, unfortunately, we don't have any PerkinElmer instruments in our lab, but I recommend reaching out to them directly, and they should be able to supply you with that answer.
All right. And have you seen or heard of any aluminum modeling to help with determining AI modeling to help with determining interferences?
I have not, but that definitely sounds interesting. I know there is a lot of interesting work that's going on with like machine learning, that sort of stuff when it comes to data analysis. We haven't really stepped into that realm as of yet, but I would be very interested to see what the newest data is out there around that method.
All right. Now I've got a bunch of questions in the chat, so I'm going to start going through those. Adrian asked, how do your tables compare to the corrections that could be applied in the Agilent software?
So we haven't gone through, at least not to my knowledge, unless Thomas has done this during the validation. We haven't compared them head to head. Again, we almost would prefer to keep everything as offline as possible, just so our analysts have a little bit better understanding of where the data is coming from.
Yep, we like to see the data. So when the black box does the magic, our auditors start to scream. So we like to be able to provide those numbers unfiltered, and then they can see the correction calculations because those are heavily audited depending on what body you are accredited to. Mm-hmm. Our next question: do element interferences differ between different instruments? For example, PerkinElmer or Agilent or Spectral, Shimadzu.
Yeah, that's a good question. They should not. Now, as one of the previous questions sort of stated, there are sort of slightly different emission lines that'll be listed between the instrument manufacturers. But this is just, the essentially the property of these elements. They will emit, at these certain wavelengths at a certain concentration. So if your instrument can pick it up, you should see it. So these interferences should be present across all instrument manufacturers.
Their responses might be different, though. One of the things we've noted is that there is a major difference between our Spectro and our Agilent because their optical systems are vastly different in design. So there's a lot of instruments use the Eschel grating, and the Spectra's Orca system. The linearity of the response is quite different, and so that'll play into the calculations. You'll just have to build a table that's instrument specific.
That's very true, and the actual, what your detection limits are, essentially, like your resolution will determine that as well. Because if you can see at a much lower concentration, then you'll probably see some spectral interferences that you may not see on a different instrument.
All right. Do spectral interferences differ between radial and axial?
They can slightly. We've in that table that we've linked for download, we've sort of demonstrated that. So yeah, you will see slightly different interferences even on the same line between viewing modes.
any instrument manufacturer better than any other in terms of interference mitigation? I
That's that's a good question. I don't know because we don't really utilize their software to really handle that for us. Um, I think it's really one of the big decisions when it comes to purchasing a new instrument is the software.
Mhm.
So if you're in that if you're ready to purchase a new instrument, make sure that you really take the time to inspect the software, get some demos of it. If you can, talk to someone who's used it for a while, and they'll probably be better equipped to answer those questions. If you can find someone that does more similar work to what you do, it'd be much more helpful to get their advice on that.
All right. Our next question is from Lisa, and it's a really good question. I was hoping this would come up at some point. Do you do daily testing for verifying your IEC table? Do you run a multi-element standard?
Oh, very cool. Yeah. So this is a little bit of a complicated answer. So the interference table that we have built, we have not validated for our analysts to simply use it to either pass or fail a blend based on the result from the interference table itself. We do run our our normal check solutions each day. So sort of like our calibration check solutions, they get run with this method. They're not testing specifically the interference table, but you do see if you look at the day by day, you will see a very definite pattern of what the interference table helps and what it doesn't. Um, so so yeah, we don't necessarily do it for ours because our interference table isn't validated for our method. It's just there to help our technicians troubleshoot.
Yeah, one comment I'll make on that is the actual standard that we're using, like as a procedural check every day, is actually what we used to use for this program before we started doing basically using this instrument. We modified the matrices. We really revamped it to make life better for the instrument and for the analysts. So we actually use the old solution as a check because basically we're transferring from method to method. As this was a good way to show that the new method works as well as the old method. Also helps with the texting limit verification because our one of our check standards is actually lower than our low calibration standard with the new method. But we do note when you look at the interference column that Mike showed on that one slide, more things pass with the interference table than without. So that's a good check to say it's working.
Yep.
All right, how often should we run a new IEC table?
That is an excellent question. So it really depends on how you're using it. Is it validated for your method? Are you using it to generate results? If that is the case, then I would look back at your validation data. Now, Thomas, did they say IEC?
Mhm.
So that might be for the mass spec as well, which we haven't really done a whole lot of work in yet. I think it's something that we're going to sort of take this method and expand it out to ICP mass spec eventually. That might be, you might have to run that more often, would be my guess, because I think there's a lot more, the mass specs are a little bit more susceptible to, um, I would say, the cleanliness of the sample introductory system than the OES can be. So you may have to rerun, if you're doing it on ICP mass spec, you may have to rerun it a little bit more frequently than you would on an OES if it's a validated portion of your method.
I would be concerned about the cleanliness of the lenses as well.
Exactly. Yeah.
All right. And just a comment from Adrian, interferences are dependent on the resolution. And yes, we definitely
Yep.
saw that on that first slide with the zinc and the iron. Um, another question. I've observed that some oh let's see. I've observed that some single element solutions contain trace contaminants that cause an issue, such as tin and indium. Yeah, and actually picked up on that with Mike's talk. He showed that there was zero point 0.1 iron or zero point 0.1 manganese in the iron, and when I saw that slide, I was thinking in the back of my mind that might actually not be iron, that might be manganese impurity because that's a common contaminant in iron. But yeah, absolutely. Do you have any comments on that, Mike, about the cleanliness and what you should look out for?
Exactly, and that's 100% correct. Getting super clean single element standards is key to really creating a really good interference table. Um, we have a pretty extreme luxury, and that's what we specialize in. So we have a lot of testing protocols that are based solely around trace metal impurity testing in our starting materials. So we have a really good profile of what impurities in our single element standards would be. But if you're purchasing single element standards, always check the certificate of analysis. They should have a trace metal impurity section on it that would sort of detail, in this 1000 ppm blend, there is such an amount of, or in this 1000 ppm tin, there is, or indium, there is a trace amount of tin and present. So that would be my advice on that one.
I'll add something to that. I know when I built this table, there were some instances I believe that came up with the rare earths more than others, where I actually saw, like, let's say it was gadolinium and I saw yttrium. We were monitoring 5 different lines for yttrium, and I saw gadolinium, is causing there to be a response for all of the lines. When it was the same for all of the lines, in the back of my mind, I was like, these are not interferences, these are contaminants. So those were, logically, we could actually exclude those from the table, because we know they're not actually interferences. It's you're actually seeing a contaminant. So if you monitor multiple wavelengths, you'll get a better idea of whether or not it's actually a contaminant versus an interference.
It's an excellent point.
All right. Well, it. Let me check the Q&A. Yep, we got some more here too. So, do you do daily testing for yeah, so we answered that one. Ah, is radial view better to eliminate interferences than axial view?
That's a good question. We have found that it really depends on the element, but most of the time, yes. And Thomas, if you want to jump into that one, you feel free. I think we mainly use axial because we can get better detection limits, but we have seen that radial will eliminate some interferences.
Yeah, my observation with the radial view is that the background is lowered, and the background actually looks different. So sometimes, even with a clean spectra of like a nitric acid blank or an HCl blank, you'll get these random bumps. And sometimes it's from like OH or other, gases that might be in the system that will always be there. But radial sims tends to get rid of those, just by nature of how it's viewed on the plasma. So what you'll see is the background points will be different. So you might actually set like a 2 point background on something, and in radial view, you might do something different. It really depends. You'll see that the blank looks different for the line, and it makes a big difference for sodium, potassium, and lithium, I believe. So if you look at those blanks and then look at those with a tiny bit of standard, you'll see that the backgrounds might actually behave differently. All right, and next, how do you determine what interference mix to use?
That's a good question. I think that might be for like a check solution. So that's how I'm going to sort of answer that one. If you've got more detail, please send through another Q&A. But if you're sort of designing something as an interference check solution, what I would do is design it around some known interferences. And again, you sort of want to get everything in it as clean as possible. So that's what I would do. And if you have any more information, please feel free to submit it via the Q&A.
Okay. And another question, do you see interferences from trace elements leached from containers, pipette tips, etc.?
Yes, that is an excellent question. So we have a pretty specialty process that we go through for all of our containers. But you will see that, especially if you are using a bottle or something off, that you're buying an empty bottle, prepping your standards up in that. If it is not leached with dilute nitric acid, you will probably see contaminants leach out of that bottle. So the leaching sort of process that we follow is we will use 1 to 5% dilute nitric, and fill up the bottles with that solution, hold them for about a week to 2 weeks, dump them out, rinse them out really well with really clean DI water, let them dry, and then that usually will take care of most contaminants out of, we use LDPE bottles, so the low density bottles. That process should be pretty similar. If you want to go even cleaner than that, we do sort of more soaks in nitric at a higher temperature, if you're really looking to try to get everything out of the bottle. But I would definitely recommend, if you are not sort of accounting for that, you will see contaminants come from bottles, from pipette tips, from essentially anything that touches the sample or standard.
All right. Right now, I have only two more questions, but more could come in. But I do like both of these questions. So, for Adrian asked, if a contaminant exists in a single element solution, but the observed response is greater than the certificate contaminant concentration, what is the recommended approach? Because yes,
Okay.
we're not
Yeah.
always right, which is why
Yes.
which is one of the reasons we do not certify trace metallic impurities, because they're low and the uncertainties would be so great on them. But Mike, what would you recommend?
Yeah, so I brought the Q&A panel over so I could read it one more time just to make sure I had the question correct. In that case, what you're gonna want to do is verify in your own lab. So it could be your sample preparation. Maybe it's something, like I said before, it was something in your bottles, it was something in the acid you're using to dilute. So you want to verify that result first. Then you were going to want to check to make sure that there's no interferences that could be present that would be making it that way, make it appear higher than what it says on the C of A. And then next I would reach out to whoever, you got that material from and say, contact them, let them know that you're seeing, a result that isn't matching on their C of A, and see what they have to say about it. It is very difficult to do really accurate trace metal impurity analysis because Thomas said they are just so low in concentration. So if it is a factor of, say it's supposed to be 2 ppb and you see 3 ppb, that's probably, they probably should have accounted for that. And that's why we overestimate on our trace metal impurity as much as we can. If you're seeing it's supposed to be 2 ppb and you see 2 ppm, that's much more of a problem. And you'll want to reach out to whoever supplied that material and sort of shore up an answer that way.
And just to clarify that question, how to handle a correction that needs to be made when the contaminant exists in the solution.
Oh, okay. Got you. Perfect. So if you know there's going to be a spectral interference present, what you can do is, my first instinct would be try testing by standard additions. And we have more information available on that on our website. So if you search inorganicventures.com and, search in standard additions, you should be able to find that method pretty quickly. So that would be my starting point. If you know there's going to be some sort of interference, switch your testing method over to a standard additions instead of a calibration curve.
All right. In interest of wrapping it up, I'll let Lisa have the last question. Do
Okay.
you run an internal standard or ionization suppressant? Would you need separate interference tables or methods for these solutions?
That's an excellent question. So we do not run an internal standard simply because we need this method to check for everything. So there was nothing that we could have pulled for an internal standard that would allow for all of our samples to be present, because whatever we picked would probably be the analyte in a sample at some point. So we decided to not use an internal standard. for this method. Now, the old method that Thomas mentioned, that we used the calibration standard as our sort of procedural check, that method actually did use an ionization buffer. It was 500 ppm of cesium was added to the standards. The samples, it was just spiked in as the samples were prepped at a concentration of roughly 500 ppm. And that worked out really well for us. Cesium didn't really have much of a, there weren't many spectral interferences that we noticed. So if you need to use that in your method, I would recommend cesium. It seemed to work out really well for us. And you did see a difference. I will say that we essentially messed up a prep in our lab one time and accidentally spiked in 100 ppm cesium instead of 500 ppm cesium for about a week, and could not figure out why everything was failing. And that was determined to be the reason, was a bad prep on our cesium spike solution. So it does make a difference, especially with calcium, potassium, magnesium, sodium, those sorts of elements. So we have done that in the past, but you would need to create a separate interference table if you're spiking those in, or if you're adding those to your solutions.
Yeah, and one thing to note, the cesium, wish it was the cleanest, but we do the best we can. One thing to always note is you expect certain types of contamination in cesium. You'd expect everything in that first column and a lot of the stuff in the second column. So you'd commonly see trace amounts of sodium and potassium, but the benefits of adding it far outweighed the contamination level. Even adding 500 ppm, the response, it really changed in axial mode. It shouldn't really help in radial just by nature of what it's doing in the plasma. And then
I think there's one more in the chat, Thomas, that I think that you would be the best equipped to answer.
Okay. What kind of rinse do you recommend between each run of single element solutions? Yeah, that would depend on, which element it is, but definitely look at my webinar from last month online. It should be on the website, but nitric works for a lot. HCl works for precious metals and mercury. And if you need something special because you're running high levels of, let's say, osmium, look into some specialty rinse solutions that might contain thiourea, hydroxylamine hydrochloride. But honestly, a mixture of nitric and HCl should do the job, especially from an OES standpoint. And every once in a while, add some HF if you're having trouble with sticky HF elements. So if we sell the standard in HF, you probably should add HF to your rinse. Hopefully you're using the HF resistant system, but reach out if you have any more questions about that.
Yep, I would also recommend checking out Thomas's webinar from last month. That was excellent and sort of went over a lot of the washout solution issues that you may come across.
All right. Well, it looks like we wrapped up in decent time. I know we're about 20 minutes over, but I think most of you actually stayed with us, so we thank you for that. Thank you for joining us live today. We do appreciate you taking time out of your busy day to learn from us, and I hope you learned something new that you can share back at your own labs. We will be sending out a follow-up email to remind you of the 3 custom standards Mike mentioned during his talk, and it will also contain some post-webinar survey questions that we'd love your feedback on. We will be skipping March to give our speakers time to prepare after a busy trade show and conference season, but join us for our next webinar in our 2022 series on April 1st. Dr. Brian Alexander will be pivoting over to interferences on the mass spec, and will likely focus on EPA 6020 and other related methods. So thanks again for joining us, and we hope you have a wonderful rest of your day.
Thank you all.